Hello?
Oh, very good. Hello? Are you hearing me?
Yes.
Hello.
Yes, doctor, but we are hearing echo as well.
So, can you see me?
Can doctor?
And doctor, but got echo.
Yeah.
Okay. So in that case, I okay. So let me explain. This is new technology using many instruments, right?
Yes.
Ah. Okay. Ah. In that case, sometimes you will help me, okay, to scroll down. Okay. So now today topic, where we reached, injective. So what? Just a little reminder. Huh? What does it mean? Injective function. Injective function. Okay. Definition says. So if function is given, here x varies from A, which is domain of f, and y varies from B, which is range. This one we denoted by R. D. So this one RF is range. RD, the second one, F minus 1 is RF range. Domain we denoted. Okay, currently dom of F, domain. So Y varies from the B, and this one we call it range of F. Okay, now this function is called it injective. We have three different injective, it's called it injective if f of x1, x2 implies x1 equal to x2. So it means for each image of x1, we have the one image in y. Okay. So injective if this f1 f of x1 x2 implies x1 equal to x2. Okay. This is the injectivity of the function. But the surjective, for the surjective if domain of f equal to range of f. Okay. So the surjective, the domain of f should be equal to range of y. So actually y varies here, x varies here. So what and the third one, actually third definition says bijective if f is injective and surjective. Injective and surjective. So bijective actually includes both injective and surjective. There is one good example. Example one. So if function is given, for example, like this, linear function, we know the domain of f, this is f, domain of f, which is, call it A, is from minus infinity to plus infinity. And in the previous class, I show you how to find the range. To find the range, we have to solve the in terms of x, 3x equal to y minus 1. And x is equal to 1 over 3 y minus 1. And change y equal to 1 over 3 x minus 1. So now this domain, this one is called it inverse. So this one is called it inverse of the function. And the domain of f minus 1 is equal to range of f, And here, minus infinity to plus infinity, which is R. The whole R is a domain of f. And whole R, this is also R, is a range of f. So range of f and domain of f is the same. So this one shows it is surjective. Now this function is injective as well. Injectivity comes from here. F of x1 equal to f of x2. It means 3x1 plus 1, 3x2 plus 1. So 1 cancel, 3x1 equal to 3x2, which implies x1 equal to x2. So it is injective. You see, this function is injective, this function is surjective. So I can conclude from this, I can conclude it is bijective function. Bijective. Okay? I think that's clear. If I take another function, the second example, can you see here also? Okay, can. I think they can. So the second function, we take this x square. Okay? So this function, domain of f is from minus infinity to plus infinity, which is R. Now I define the range of f. How I define? If x belong to minus infinity to plus infinity, I am finding the domain. So x square lies from 0 to infinity. So this is f of x from 0 to infinity. So the range of f is from 0 to infinity. So from here we can see domain of f not equal to range of f, not surjective. So not surjective. Not surjective. So this function is not surjective. Now what about injectivity? Okay, I will check the second. This is the first one. Now second one, injectivity. F of x1 equal to f of x2, which is x1 square equal to x2 square. So from here, I can get plus minus x2 by squaring root. Thank you. Yes, please you pay attention. Why participants 61? Before it was 63, now 61. Okay, now you see, so it means x1 not equal to x2. So this function is not injective. It is not injective. Okay, now please do pay attention. So this function I will consider in this interval. X belong to 0 to plus infinity. I do check the same function on the different, which is, this is a domain. Okay, this one, domain of f, I am saying is this interval, not whole R, just part of the R. So in this interval, so I will, so when x lies from 0 to infinity, x square also lies in the same interval. It means f of x from 0 to infinity. So it means range of f is also from 0 to infinity, which is equal to domain of f. Domain of f. So now this function, please pay attention, this function is surjective. 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 Now, second part. F of x1 equal to f of x2, which implies x1 square equal to x2 square, implies x1 equal to x2. Why? Because x1, x2 is here. If it is positive, square is also positive. And this solution gives only the positive one. You see, the negative we cannot take. Okay, so we will take only positive one because x2 is positive. So plus square root of positive, x1 also positive. Sorry, this is plus minus x2 without. So I will take only one. Understand? So you see, the same function in the considerable the interval or the domain, it might be injective and surjective. So it means it is bijective. Okay? Very nice example to understand what is the injectivity and bijectivity and surjectivity actually. So if injective and surjective, then it is a bijective. Okay? Biject comes in the last. Okay, so now today actually I want to show the next theorem. F is injective, then f minus 1 also injective. Okay, corollary 1, 1. So I will remove everything. So it is said corollary. If the function f is, corollary says, if f mapping A to B, of course f is a mapping, is injective, then f minus 1 mapping B to A is also injective. Very important corollary. How we prove? We take element from the R. Okay. Actually here B is the RF, okay? B is the RF, A is a domain, okay? Look, A is a domain, B is the RF, okay? Here it is written. So the for the proof, what we do, let's say A is the injective, huh? Because here it is, if A is injective, then I want to prove. To show that this one injective, I need to show, you know, this one I have to show. I will take the two elements, then show that y1 equal to y2. Because of this F injectivity, I can show that y1 equal to y2. I need to prove this. So to prove this, what we do, we choose, take element y1, y1, y2. Okay, take two elements, y1 and y2 from RF, because R1, y1, y2 belong to the RF. And so it says that say this RF, and so suppose that look look, f of minus 1 of y1, f minus 1 y2, actually this is the element of x from A. You see, y1 is the element of RF. This is a x, this is a y. So y1, y2 belong to the y. F minus 1, when we act f minus 1, we will get element of x. So that's why, you see, now I am saying that f minus, for the injectivity, I should do like this. So you see, from this is element of x. Now I have to show this y1 equal to y2. Okay, so this is we take, then f of x is equal to y1 and f of x. So from f of, if I act f function from this part, f of
Sorry, doctor, we can't hear you.
Sorry, doctor, I can't hear your sounds.
Okay, now divide.
Hello?
Please. So can you see? Can you see?
Yes, doctor, can hear you now.
Okay.
Yes, can hear.
Okay. Generally, did you understand the point? You see, I want to prove this. So actually, here there is a proof. Take 2 points from RF. Here, acting F, we will get. Actually, this equality means this 2 element has one image, pre-image, one pre-image. Implies, you see, X from the first equation, from the second equation, it got like this. Since F is injective, here F is injective implies y1 must be y2. So that is a proof of this theorem. You see, if F is injective, F minus 1 is also injective. In other words, for every element of y1, y2, there is one element in x, x1, x2. Okay, for each element of y1, we have one element y2 in x. Okay, very good. So next one is for any f. The inverse from B is a function if and only if f is bijective. Okay. Are you okay hearing me? Hello.
Yes, doctor.
Okay. So in that case, we will go to the next theorem. Okay, good. So this is a proof of this corollary finish. Okay, next. So second corollary says if F, corollary 2. This is corollary 1. Corollary 2. 2 else or 1 else? Corollary 2. Says that if F is the inverse is from B is a function, any F and inverse is a function if and only if F is bijective. Generally, if F is bijective, if F is bijective, then I am just a little bit reformulating. Then F mapping A to B and F minus 1 mapping B to A is a function. Okay, can I formulate like this? The inverse is a function if and only if. If and only if. Then is a function. So opposite. If f and f minus 1 is a function, then f is bijective. Okay, I will do like this. If and only if f is bijective, then is a function. Okay, that formulation is more proper actually. What I'm going to say here, you see, the bijective actually, it is if the proof. If let f be bijective first. Let f be bijective. So it means it is injective and surjective. So now I have to show that f mapping A to B and f minus 1 mapping to the B to the A is a function. What does it mean, the function? Definition of the function. If you remember, on the top, there is a definition. The f is called function if two conditions satisfy. To be a function, so there is two conditions. One, for every, if I'm not mistake, for every x in A, there exists y such that this relation holds. Second, if we take 2 points y from binary relation of I think f and x z from f, then y equal to z. If I'm not mistaken, this is a definition of the function. To be a function, so for every x there exists y. This y is from B, such that this relation holds. This is the function of a definition of the function. But this one actually another point of the definition of injectivity. You see, so for two different, I can say here y1, y2. It is better to say y1, y2 implies y1 equal to y2. You see, so when binary relations, then y1 equal to y2. So to prove this theorem, what they say, in general, the inverse function what inverse function what is not needn't be a function. However, if f is a both one-to-one function and onto, then f minus 1 is a function from B to A and is called the inverse function. Actually, proof is not proper, just general statement. In order to prove properly, you see, if it is bijective, we should show that function f satisfies this. Okay, f function, okay, because f function is a biject means injective and surjective. That's why this one holds for f. But what about f minus 1? F minus 1 actually mapping B to A. B to A should be injective. Okay, I think this one I can just confirm because of previous corollary. If f is injective, then if f injective, then f minus 1 is injective, right? Is injective. Corollary 1. If f is injective, then f minus 1 is injective. So from corollary 1, we can say f minus 1 is injective. So if it is injective, it means it is a one-to-one, and since f is a bijective, means surjective, the f mapping A to B, surjective implies f minus 1, which mapping B to A is surjective. I think this is the general proof of the theorem. we cannot prove like this, as above. We just use the corollary one and the definition. So that's the proof. Now important one is the next theorem, theorem 1.4. Suppose that f mapping x to y, and a and b is be the subsets of x, and c is a subset of y. Then, very interesting point, if f is injective, then for any subsets a and b of x, that theorem is interesting theorem. Okay, can I remove this? This is the definition of the function. Bijective implies injective and surjective. Okay. Here I will show the examples, okay? So now next is the theorem. I can show the theorem, proof of the theorem. So you see the injectivity and surjectivity, which is bijectivity, actually plays very important role in many things of the theory. Okay, so now theorem 1.4. I will just shortly write the 1.4. So I don't formulate fully. Interesting point I will show. So f a union b can be equal to f of a intersection b, not union, intersection. You see, under that conditions, if f is here f mapping x to y, and a and b is a subset of x, and c is a subset of y. So this condition is needed. C is a subset of B. If f is injective, so this equality holds if f is injective. Okay, so this injectivity, injective. Do you remember? It is, if you remember that the theorem 1.1. In the theorem 1.1, okay, proof. Very nice proof. Theorem 1.1 stated that for AB, A intersection B, f of A intersection B is a subset of f of A and intersection f of B. So theorem 1 is given this. So now to prove this theorem, to prove this, now if you remember, I took element from here and show it is an element of here in the theorem when we start proving. But opposite we couldn't prove. Actually, opposite way we couldn't prove. And the condition we have proved it. So that's why we say that this the inclusion for any function is correct. But when function is one-to-one function, equality holds. It means element of right side is the element of left side. Element of left side is the element of right side. Okay, so now here we will prove that if we take the element from the right side, how we get it is the element of the left side. Okay, very interesting point. I will prove actually both to remind you the proof both. But first, let me show the second one. So we take one element, okay, y, f of a intersection b. Okay, we take the element from the right side, any element from the right side. Yeah, from the not left side, from the right side. F of a intersection f of b. By the definition, what does it mean? Y belong to the intersection. It means y belong to f of a and y belong f of b. Okay, this one hold. Next, it follows that x1. Okay, now it follows the exist point. Okay, x1 and x2. Okay. So look, I got this. What can I say? They exist. It followed that since f exists point x1 from A, x2 from B, such that f of x1, f of x2. Okay, now look. By the definition, what is this? It is a function of x such that x belong to A. Okay, so by the definition, it is a value of all f of x such that x belong to the B. So by definition, there exists x1 and x2. Okay, x1, x2, such that x1 equal to f of x1 equal to f. No. There exists x1, x2 such that y equal to f of x1. There exists x1, x2 such that y equal to f of x1 and y equal to f of x2. So here, interesting point, here x1 belong to the A and x2 belong to the B, right? x2 belong to the B. Okay. x2 belong to the B. And A and B is a subset of X, which is domain. So by definition, since it is a function, so there exists x1, x2 such that y equal to f of x1 and y equal to f of x2. So x1 belong to the A, x2 belong to the B. Okay. Now since f is injective, okay, please pay attention. Since f is injective, so means f of x1 equal to f of x2, which is y, implies x1 equal to x2. Okay, please pay attention. This is also very correct, nothing wrong, since f is injective. So this one holds. Now look, interesting point is here. Here I say x from A, x2 from the B. But because of injectivity, x1, x2 should be equal. And this implies So x1 I will take belong to A and B, the one of the intersection. The x, I can take the any x, which is I can take any x from this, pay attention. X belong A and intersection B. Because 2x, coincides, and if x1 belong to the A and x2 becomes, you see, this one I will formulate like this. x1 belong to the A and x1 belong to the B. You see, here separate. But because of this equality, x1 and x2, which is one element, belong to the A and B, which implies x belong to the A intersection B. Okay? Now, if I take f from both sides, belong to f, we usually say that when we take the f, it is a subset of f of A intersection B. Okay? So f of x is maybe I can take this is y element belong to, I think better say like this, when I take f, it gives the element y. If gives the element y, so this element belong to the f A union B. Look, I reach y belong to the f A union f B implies y belong to the f of A plus A union B, A intersection B. You see, any element from the right side, I have shown it is the element on the left side. In the theorem, we have proved only one side. Any element from here, we get element of the right side. And very good analyze it one example, right? So if you remember how we proved the opposite one, let me remind you how to prove the first part. So I will take element from the left side. Take y from the left side, f union B. According to the definition, it is the element of f of x such that x belong to A intersection B, according to the definition, right? So since x belong to A intersection B implies x belong to A and x belong to B, it implies. So what about f of x? F of x, which is y, belong to f of A, and y, which is the f of x, belong to f of B. Look, y belong to f of A and y belong to f of B, which implies y belong to f of A intersection f of B. You see, if y belong to this, according to this scheme, you see, according to this scheme, acting the f function from here and from there, I can get y belong to the f of A and f of B. So vice versa also proved. So the theorem is completely proved. But please, how you prove the second one, third one? It is there, but please do. Okay, one I will show you. The last one I will leave it for you. Okay, how to prove the second one? Also, actually, it is nice. The first part is already proven in the preposition 1-1. You see, 1-1 says that the proof, actually, I am proving proof of this f minus 1, f minus 1, f of a is equal to a. Okay, now I am proving this equality. Proof. So this one is given. A is a subset of f minus 1 of fa. This one is given from the previous statement. Okay, previous statement. This is given, preposition 1.1. Okay, now if it is given, it means if we take any element from right side, is the element of the left right side. Now we will take any element from here, and we show it is the element of A also. You see, previously we have shown this. Now let me take element from here. What does it mean, this element? So f of A is a y. So I will take x from here, f minus 1, f of A. I take one element from here. So then what will happen? Then f of x belong to the f of A. I will x f both sides. F of x becomes element of f of A. Yes. If I act, you see, if I act f of f minus 1 is identity f of A. So this is element y actually belong to the f of A currently. So next, so this is the first step. Second step, this is done, f of more. Then we have assume that, okay, you see here they use what we call it contrapositive method. I think without using the contrapositive, can I prove? Let me try first, okay? If not, then we have to follow that. Okay, contrapositive method they use. Just because here f function is an injective, because the injectivity, maybe we can prove that the x belong to the A also. Okay. So this is like this. If I so I'm taking the element from here. Now I want to show it is the element of there. So if I act f minus 1 of y, which is element of x, this is the element of x, x equal. If I'm acting the f minus 1, so it is the element of f minus 1 of f a. So again, I'm taking the same. You see, from here I cannot get that it is the element of a. Now here you see I'm getting the same thing by applying the f minus 1. I am getting the same thing. So now I think no way to show that the X is the element of A is not direct. Huh? So actually, by definition, it is a all element of X such that X belong to the A. X belong to the A. But here we have element of Y. Here we have element of A. Okay. So I think cannot prove by using the technique. Okay. Because if I'm acting the F minus 1, I come to this inclusion again. So actually, I have to show the element of this is the element of A. And element of A is the element of this. So opposite, vice versa. The first part is shown. First part is shown from previous one. Now that's why we have to follow this. Assume that X belong to the A and fix Y from A such that okay, now assume that it is said, assume that X not belong to the A. But why is they taking Y? If usually Y is the element of P. We cannot take element Y. I think here I will little change. Assume that X not belong A, but X1 belong to the A. So I will take one element outside of the A and inside of the A. So I'm taking the two elements because here the injectivity is important. If I take two elements, then acting to the f of x from A such that so assume this 2 and fix that one from A such that f of x. Okay, now what will happen? F of x, if I act this element by f, I will get element y. Element y from the B. This one is from the B. Okay, and I will get another y1 if I act the second one. You see? So I will get another element from the second one. So I think here better say x1, x2. I'm taking one element from A, one element from there. y1 and y2. I think this way is more proper. Take one element outside of, inside of. And acting F gives the element of y1 and y2. Then here important one, since F is injective, injective means applies that f of x1 equal to f of x2 implies x1 equal to x2. You see? X1 equal to x2. From here, I can make conclusion. X1 also belong to the A. You see? Because of injectivity. So if I'm taking two elements from A and outside of A, because of injectivity, these two elements are equal. So it means X1 must belong to the A. But here by the assumption, it does not belong to the A. You see? It means if function f is injective, then the x1, x2, they belong to the A, and it shows any element from A is the element of the now I am taking element from here, any element of here, then so after that what? Okay. So the f of x1 x equal to y. It is contradiction. X we have okay plus f of f minus 1 and prove it. Okay. Please pay attention. We came to contradiction. Okay, x1 must belong to the A. If x1 belong to the A, so then this x belong to you see, I think this injectivity implies that element of x belong to the right side, implies x belong to the A as well. You see, if I say x, one of the x not belong to the A, but because of injectivity, we have shown that it must belong to the A. So now you see from this relationship, when I take okay, look, when I act inverse to the y, I will get the element of x. Okay, look, when I act f minus 1 to the y, I will get element of x, right? Element of x. But this element of x must belong to the A because of injectivity. Okay, I hope because of this, we can say that the part B or the II is correct. You see, injectivity changes many things. So this belongs, you see, this inclusion becomes equal. This inclusion becomes equal. But if you remember, the next theorem, when we have the f minus 1 of, you see, for the f minus 1, without injectivity, it is correct. This equality holds. Please pay attention. If f minus 1, without injectivity, this equality holds. But for the f function, doesn't hold. That is the differences between the mapping of inverse and itself function. That is a big differences. Okay, I hope if you understand these two important points, just 5 minutes relax, then we go to the next another theorem. By the way, I think before starting the next page, I want to give the solution of quiz 1. Okay, because I almost check it, or almost finishing. Tomorrow maybe I will announce. But over there, most of the students make mistake in the first question. Many students solve it the second question. The induction method is okay, you understood. But the proof of the first fail. Most of the students fail. I will show you the proper answer. Take into account that how to approach. Okay, you see, here also proof is not straightforward. So you need to imagine y going here, x going here. So this relationship goes there. You have to imagine what is the process going on. Okay, so just 5 minutes relax. Then I will show you the quiz. After that we continue. Okay, thank you. Alhamdulillah, it is right here. Okay, if you remember, so for any xy from R, positive, negative, doesn't matter. This inequality holds. How to prove? The many students actually prove wrong. The first, for any xy from R, we have x am I right? Look, for any xy from R, the x is not greater than absolute value, y is not greater than absolute value. Then from here, we can get x times y is also not greater than product of this. This is from axiom. Okay, from the axiom. Which axiom need to state here. So generally for any xy satisfying this inequality, this one holds, right? Now, I am taking the left side, x plus y square. X plus y square. By the way, x square equal to, also we have this equality. When squaring, equality holds. Without squaring, we have inequality. Okay, so if it is so this is x plus y square equal, by the formula, 2xy plus y square. Next, x square is absolute value of x square equal plus 2 absolute value of x, absolute value of y, plus absolute value of y square. So now it is x plus y square. Taking square root from the both sides, because this is positive, taking square root, I will get x plus y less than absolute value of x plus absolute value of y. Okay, I think this is the simple and short proof. But I saw some students use this, but they never use proper techniques of above. You see, x square is like this, blah blah blah. Don't have. Okay, now what about the second example? Second example, if I'm not mistaken, it was it needs to prove that the question 2 was prove that 1 plus 3 plus and etc. to 2n plus 1 equal to n plus 1 square. This one many students prove properly. Proof. For n equal to 1, I will check n equal to 1. 1 plus 3 equal to 1 plus 1 square. So it is correct. 4 equal to 4. Assume, but here also many students didn't do proof. Assume n equal to k is correct. For n equal to k is correct. It means 1 plus 3 plus 2k plus 1 equal to k plus 1 square. Okay, because for each step I'm giving the marks. Mark. So this one, assume holds. Now, n equal to k plus 1, we have to show k plus 1. So when n equal to k plus 1, 1 plus 3 plus and etc. plus 2k plus 1 plus 2k plus 1. K plus 1 plus 1. Take the left side equal for this side. I will put this equality k plus 1 square plus 2k plus 3. So if I open up, k square plus 2k plus 1 plus 2k plus 3. Or it is equal to k square plus 4k plus 4, which is k plus 2 square. Or I can write it is k plus 1 square. You see? K plus 1 square. So if it is k plus 1 square. Okay, this is a proper proof. But this part many students prove, but they never, many students first one okay, but second one they didn't state it. They just n equal to 1 and n equal to k plus 1. And suddenly use this one. But here we have assumption, okay? So that's why it is also not proper, not complete solution, but this proof is okay over there. Understand?
Other alphabet than A, right?
Yes, for example, M, also okay. For example, T is also okay. But you have to assume n equal to k is correct. And for n equal to k plus 1, you have to reach this inequality when n equal to k plus 1. You see? K plus 1 square. This one is the final.
You don't need to change back A to the N. Because basically N plus 1.
Since it is given n, better say n equal to 1, n equal to k.
We don't need to change.
If you use here k for k plus 1, also okay. So you will say k equal to 1 correct, k equal to n correct, k equal to n plus 1 need to prove. Yes, but if it is given in terms of k, for example, if you put 2k plus 1 like this. So you see, this is for the odd terms. Do you have any idea of this? 2 plus 4 plus 6 plus 2n. Do you have formula for this? Okay. You can see how we get the summation. Huh? So this one is the arithmetic progression. So 2 plus 2, 4, 4 plus 2, 6, and so. So for the arithmetic progression, first term is 2, last term over 2, and how many terms? You know? So number of terms is n, right? Because 2 plus 4 up to 2n, the number of terms is n, not 2n, half. So if you calculate this, 2 to cancel, n plus 1. You see, I got for even numbers. Now I need to prove it. Okay, this is from arithmetic progression. Now for the proof, you should say when n equal to 1 means n equal to 1, 2. When n equal to 1, I have 2 on the left side. On the right side, n equal to 1 plus 1 is 2. Correct? So I will assume n equal to k is correct. which means 2 plus 4 plus up to 2k equal to n and k plus 1. Then next you have to prove. Okay, if you show the next is correct, then it is also correct. Okay, so actually all these formulas according to the arithmetic progressions. Remember, arithmetic progressions, the nth term is first term plus last term over 2 and number of terms. Okay, here please pay attention. AK minus 1 plus D. Every time we have to like this. Or another one, A2 is equal to A1 plus 1 plus D. A3 is equal to A1 plus 2D. So from here I can get AN equal to A1 plus N minus 1D. So this is main formula for arithmetic progressions. Arithmetic progressions, okay? So please revise arithmetic geometric progression very well, because it has very proper, you see there's summation, the partial sum of series is equal to exactly like this if it is arithmetic progressions. For the geometric progression also we have the nth term of the geometric progressions. Okay, for geometric sequence. Okay, anyway, I hope this is enough. Now let me go to the class.
Doctor,
Yes.
how about the another quiz question, the additional one?
Additional one, actually I today didn't bring my solution yet. Okay, because only 2 students solved the second questions. I will show you. I will give you the solution. Okay.
Okay, doctor.
Currently I actually forget to only I check the first questions. Okay, I hope everything is okay. Please pay attention. You need to know how to proper proof. Okay, my concern is to teach you how to proper proof. Okay, now let me go to the next part of the lecture. Actually, a lecture you can see is not very easy. Everything is related to. So at least let me finish the first part. So if we have the 2 functions before composition, actually there is one more. Before composition, we have restriction. Okay, because before composition, what is the restriction or extension? It is usually we call it extension of the domain. Okay, just please pay attention. For example, if I have this function, usually we say this function domain is R minus 0, or we can say from minus infinity to plus infinity, subtract 1 point. Okay. Now I will construct g of x function such a way it is a 1 over x for any x in R minus 0, and it is 0 if x equal to 0. Usually this one is called extension. The what we call it undefined point, we remove it and put it some value. So that one is called extension function. Okay, shortly like this. So definition over there. If f is a function from a to b, c is a subset of a, the function g maps from c to b. You see, c is a subset of a. Okay, then g of x equal to f of x is called the restriction of f, or the extension of f. Okay, extension of g to a. So the function define it, for example, like this one, 1 over x. Maybe define it like, I think this is more proper. Okay, the extension function of g. So actually, in other words, I can say extension function coincided with the function f almost everywhere. Almost everywhere. For all x in A except some point. Finite point. x1, x2. In general, I can extend like this. You see, function g, the new function which we are constructing, coincides with f of x everywhere except some points. Then at that point, we have to top up the values. That is the extension. Okay. Usually, you know, extension. Here, you know, I am actually this one is not very proper extension. Usually extension is like this. Look, for example, my function is given like this: x minus 1 over x square x square minus 2x plus 1. Look, so this function, if I properly rewrite, look, x minus 1, this is x minus 1 square. So if I cancel it, okay, it x minus 1. Okay, x minus 1. So actually x equal to 1 goes to infinity, brings to infinity. Actually, this one also not proper. I should do opposite. So here x square minus 2x plus 1. Here x minus 1. So as we do above, it becomes x minus 1. But this is not equal. This is not equal. It behaves. This function behaves like x minus 1. Behaves. Because this, okay, look, at point 1, this y, f at point 1 is not defined. Is not defined. Okay, this one is not defined, but this function is defined at 1. You see, behaving. So this function behaving as x minus 1, but it is not equal to x minus 1.
What does it behave?
Behaving. Very good question. So now look, I'm extending this function like this. It is equal to f of x if x not equal to 1. Then if x equal to 1, then 1 minus 1 is 0. 0. So look, if I want to draw the graph of this function without this, it is very complicated. I will take the x value, put it, cos square, blah, blah, divide, and blah, blah. But drawing this function is very easy. I will take the 2 points. For example, when x equal to 0, it takes the minus 1. Minus 1, this point. When x equal to 1, it is here. So the graph of this function, so this is gx. You see, actually, this function behaves as this function, except 0. So you see, now it comes like this, jumping at one point, and continuing as this function. Now look, this function, if I draw the graph of this function, so when it divides at point 1, yeah? Here 1. So I have the vertical line. So on the right side of the vertical line, we have this graph. You remember? So this is the graph of this function on the right side, and this is goes to up, the unboundly. This one going to the 0 approaches when x tended to infinity. So when it is minus infinity, so it approaches but never cross. It is approaches but never cross. So this function, look, this very complicated function actually behaves like 1 over x minus 1. So after simplifying the function, actually this function is much more simple than that. Much more simple. So it means this function behaves as this function. But, you know, I cannot extend this function according to the definition. You see, according to the definition, 8.1, if I say, so it is f of x, if x not equal to 1, and if x equal to 1, it is 0. So, look, graph goes infinity, negative infinity. This is plus infinity. But I am saying it takes this value at 0.1. This is also, in general, some kind of extension, but real extension, usually we put the limit function of the problems, limit point of the problems. You see, here, this function behaving like this, but this function is defined at 0, at 1, as 0. You see, exactly I put at 0, then this is continuously continuing the function. If I put here 0, 8.1, not here, here. 8.1, I don't put here 2. So in that case, if I put 2, so this function up to here, okay, jumping, then continuing. It is a jumping function, not continuous function. So usually extension function is a continuous function, okay, by behaving. Almost finishing, huh? Okay, so let me just explain what is the composition function, okay? And finish the equivalent sets. I will. So in the composition function, please pay attention. The two functions involved, okay? Okay, good. Hey, Jazakallah, you help me a lot. Otherwise, technician, I can wait until end of my lecture. Okay, so just 5 minutes, regarding to the composition. For the composition, so two functions involve, and you see, one function maps by the definition. You see, f function maps A to B, and the g function maps B to C. Then the composition, look, the composition of f and g, usually we put like this, okay? The composition we put like this, equal to g of f of x, okay, f of x. So now the composition of f and g maps from where to where? G and f, A to S. Okay. This g function maps A to C. Look, F mapping A to B. G function mapping from B to C. So this composition function maps from original A to C. Okay, that is the differences than ordinary function. So, but interesting point, this F and G, which is defined by this. Now look, the composition of G and F defined by this. This maps what? Okay, G, look, G maps B to C. F maps A to B. Now, this F and G. So if G maps B to C, F maps A to the B, then can I say this one also maps A to C? So actually they are not equal, but important thing, okay, one moment. They are not equal, but still the mapping from A to C, I think. Okay, we can define the composition as this function. Okay, no problem. FG, not that. Actually, the domain of composition function is A. Please pay attention. Domain of the composition function G and F, please, is equal to df, which is A. Domain is the same as F. Okay, this is example. Okay, no problem. So here, what I am going to say, so we conclude that not equal, the composition is well defined whenever Rf is a domain, is a subset of the domain range of F is a subset of the domain Tg. Is well defined. Okay, I hope both function, both function F and G and F actually maps A to the C, because G maps B to the C and this one A to the B. So this one, but they are not equal. Okay, so this composition of G and F X is not equal in general. In many cases they are coincides also, but in some cases not coincides. They are not equal. There is one good example you can see. They are not equal. One is 2x plus 1 square, second one is 2x square plus 1. So they are not equal. But here it is said that RF, domain of composition, not domain, the range of the composition function is a subset of domain of G. So this inclusion also important. You see, domain, the range of composition function is a subset of domain of G. Okay, and the last 3-4 the remarks you can see, if F and G are they both injective, then composition is also injective. If FG both subjective, then subjective, the G and F also subjective. If F and G both bijective, so is. And the last one, if F is injective, then the inverse composition is equal to X. For all X belong to the domain of F. And F and F minus 1, also X, for X belong to the RF. You see, important one. So F minus 1 composition F, and actually look, is the same phase F and F minus 1 of X is the same X, but domain is different. Okay, domain is different. For the first case, it is domain X belong to the DJ. In the second case, it belong to the RF. So only X belong in different places. Okay, so please, if possible, prove it. Otherwise, memorize it. Memorize it. Okay, that's all. So now time is over. If you don't mind, we are going to finish, right? 12 o'clock? Yeah, 11 o'clock, right? 11 o'clock. Okay, that's all. Thank you for coming. Today, I have 3 students in the class. Thank you. You see, otherwise, 3 technicians also. Good. Thank you very much.
Like the
Okay.
Thank you, Doctor.